Okay, let's continue with this third part of the presentation. Although we'll just start this subject, we'll continue next week with the remaining. We'll actually do some introduction in this observational method design in geotechnical engineering. I'll just try to introduce this term, as it's really popular, not only in the worldwide practice, also in the local practice. A lot of the structures, a lot of examples of the construction in the landslide area were constructed and designed by using so-called observational method design. When you say design, we mean some process of selection of construction geometry and construction process. It can really be done in different ways. And a first example is so-called conventional design and construction. Conventional design and construction means the design do not change. The design do not change. What it actually means in practice, when you do the design, you prepare some technical description, you prepared some calculation results, you prepared drawings, and you prepare the bill of quantities, and then you get it all to the contractor, and he start following the instruction from the main design. And at the end, from the drawings, you get this. Actually, you get this. This is final product that is absolutely the same as the one you draw here. So you define the cross-section thickness, you define the reinforcement, you define the construction sequence, like excavation, construction of the wall, backfilling of the wall, installation of the drainage. So everything as it's shown here. So what you draw, you have at the location absolutely the same. This is conventional design. This is something what can bring a lot of problems if you go for this kind of construction for a very much serious, complicated, more complex structures like we always have when we design and construct highways in landslide prone areas. So this observational methods means forget about conventional design. Actually, it means you have to update the design as you receive additional information. So you have some initial investigation works, but then you start the construction. After you start the construction, you receive additional information regarding the condition of the excavation. You are doing the measurement of monitoring measurements. You receive those information and you update your calculation and you update the drawings. And then you have another you have final solution that is more appropriate for the real observed condition and at the location. But prior to before we go to details of this observational method, I'll just give you an introduction, few slides defining the principles of design, the concept of design, different designs and construction that are used, and then at the final phase of this lecture, we'll go really to this observational methods. Probably not today, but next week. So when we talking about design methods, not observational methods, but some conventional like design methods, we have two options. First one is predefined design, that is so-called approach one, and second one is just to use experience for defining conceptual design. According to Peck, this is called gambling. So you just use experience. You say, okay, in these conditions, 5 years ago, I used the construction, I designed the construction like this. We constructed this structure and it behaves good. It's stable. But okay, because I saw that, let me do the same things here. But that could be more than gambling, because the conditions we had at the location 5 years ago doesn't have to be the same to this location. That's why we usually go in the conventional design. We usually go to this predefined design where we define the typical cross-section characteristics of the material. We do some assumption, we do the calculation, and we prepare the drawing. What is the problem with this approach one that may be considered really appropriate and correct? The problem is that it can sometimes be spending more money approach. What does it mean? It means that this wall, for example, this example, I could say, okay, I won't do any investigation works. I'll just check on the condition of this soil. I'll say, okay, it may be some C5, it may be some soil C23, and let me design this wall, the sliding stability, overturning stability, bearing capacity, global stability, and it will define some wall that has the geometry like this. But if it's appropriate for the condition, I may go not for this approach. I may use observational method approach, and maybe I could spare some money and not construct the wall as it was according to these assumptions. However, in both these approaches of conventional design, the monitoring plays a passive role. What does it mean? If we, for example, I don't know, we can put some fixed point here and here, and we can measure the displacement of this wall during backfilling of the material here. And for example, we measure that this wall displaced laterally 2 millimeters. Okay, very good. It's 2 millimeters. What now? I have information. This wall has moved 2 millimeters in the horizontal direction. I spent some money for getting this information. But what am I doing with this information? That's how investors are thinking like. So they don't care if it's 2 millimeters or 4 millimeters. It may be useful information for a designer. So he knows in the future, okay, I built the wall like this, it moves 2 millimeters. Now I can build the wall maybe with this footing that is 30 centimeters narrower than this. It will then be 4 millimeters. It will still okay. But for this construction, for this retaining wall, the monitoring would play the passive role. Not in the observational method design. The monitoring is really active. Any information we received from the monitoring during construction, we use it as input for additional updated design. Okay, but first of all, and now I'm trying to concentrate on this traditional design approach. And what we usually do is practice is this: we have predefined design. We define everything, and then the construction follows what we define according to some assumption. I'll now show you a few examples of this design approach, this predefined approach. Sometimes it's too conservative, sometimes it's spending money approach, sometimes it causes large problems. I'll show you a few examples of highway constructions in a landslide area. The first one example is from this near between Doboj and Banja Luka, this highway route, where we had a situation like this. This was soil-like material, and this was soft rock material. It was observed that the sliding occurs like this in natural conditions. So the existing slope was near the safety factor equal to 1, near the sliding. And the excavation had to be performed like this. So this was the highway route like this. And here it needed to be constructed some retaining walls. Since up above here there are a few houses, and it could fail due to this excavation. So the solution like this was designed. These were piles here, piles in this area between one and the other line, and up above it's the beams like you see it on the figures. It's like this, and this is how it looks here. Here you can see piles. The piles are also here, and these are the beams. The solution was relatively expensive. The approach was relatively conservative. It's assumed that all of this is really sliding, since the results of some inclinometers exist prior to construction. It was really constructed as designed. Any line that was drawn was respected by the contractor, and it was really constructed at design. The construction period was very short. That is good. That is favorable, but it's relatively expensive, so that's not favorable. No significant problems were observed during and after the construction, so the design may be considered as correct. What is the lesson after this? Well, maybe observational design could introduce some cost reduction. Maybe after the drilling of these piles, some additional information were known about this location, and maybe the piles could be a bit shorter. Maybe the spacing between piles could be larger. Of course, this this could reduce the cost, but maybe it would introduce some problems to the dynamic schedule of the works. So at the end, maybe with this information, this can be considered some successful project. The other problem, practical example two, once again approach one. This is the abutment of the viaduct, and this is the approach to this viaduct. Large embankment was about to be constructed, like from these gabion walls. You'll see the cross section here. So this is the design solution. This is the highway route that connects to this viaduct abutment. This is the 1 to 1.5 slope, and this is gabion walls at the bottom. After the construction reached this line, a sudden failure occurs like this. This failure, you can see it here. This is the toe of the landslide. This is total destruction of the gabion walls here. Problem becomes more serious since 10 meters below this gabion wall, there is existing gas line, this gas line pipe that could bring catastrophic consequences if the sliding continues. That's the cracks at the near this abutment. So this is here. You see here the abutment. You can see it here. So it's just a figure photography from here. So you can see a typical cracks indicating the sliding all this area from here to down. Immediately after this failure was observed, this material was removed from here by excavating. You can see this excavator removing this material, since this is the surcharge load here. So it's immediately this was removed. All this area to reduce this surcharge load from here that influences the sliding. And then the sliding relatively stops, and these are the conditions 2 or 3 months after failure. You can see this line, you can see all this dropping down, and this global stability of this embankment was the problem. What happened later? This all removed. The deep foundation, when it is introduced, 2 lines of board piles of large diameters with a capping beam, and as a retaining structure, concrete wall was built up to construct this. So what could be the lesson? The lesson is that there would not be significant cost reduction even if we went for a observational method, since no doubt in these conditions this deep foundation had to be done. But maybe some construction time reduction could be significant and could be an option if we decided to follow the displacement, to monitor displacement during construction, as soon as we recognize some increment of the displacement prior to this phase, maybe 2 or 3 months before, when the embankment was here, we could introduce maybe some deep piles here and here, and to support this sliding, to prevent it, that causes a huge construction time increment and quite a lot of problems for investor and for contractor of this route. Okay, the following thing is now to introduce observational methods and to discuss about it, to also show some practical case study where observational methods were successfully used. So the plan is to discuss about it next week. Now I'll use these 10 minutes, 5 minutes to show you this assignment we agreed to send to you. I'll send you the assignment along with this video material as I sent it last time. So I'll put video material from today along with the assignment. But now I'll just spend 5 minutes to show you what's the detail of your assignment, so you can already start to preparing some draft. And if you have some question, you can ask me during the lectures next week or week after. So the assignment is very short. It's on the one page. What is it about? It is about slope. So this is the slope geometry, and this is some surcharge strip footing at the top. This is actually can you see this? I think I shared my desktop screen, but just if you can confirm that you can see this.
Yes, yes.
Yes.
Okay.
Yes.
Okay, I'll give you I'll I'll give you as an assignment this the geometry and geotechnical characteristics of the materials involved in this small scale model. So it's a small scale physical model that was that was constructed, that was performed. It's, you see, half meter height on 1.14 meter width, and it is surcharge at the surcharge load at the slope. You have all the information here. So it's a small scale physical model that was prepared to investigate load settlement behavior and ultimate bearing capacity of strip footing near the edge of the slope. So this is something that looks like potentially unstable slope. When you surcharge it here, it may fail like this. This is typically what we have when we build highway foundations at slope area. So, but this is not a full scale model. This is laboratory model. And all the geometry is defined here. The slope angle is beta 30 degrees. The strip width is 7 centimeters. So it's a small scale model, not 2, 3, 5 meters strip footing, but small scale, only 7 centimeters. This is made of steel. So this is 2 centimeter thick steel plate. And it was located 21 centimeters, three width of the footing from this edge. So you have all the details about the geometry. The geometry of model is shown in this figure 1. So this is a layout plan, ground plan, and this is typical cross section. This is the load frame, and the surcharge applied vertically at the top of this steel plate. The material is also a model sand. It's a medium dense sand with the geotechnical parameters shown in this table 1. So we have unit weight, internal friction angle, cohesion is 0, Poisson ratio, and Young's modulus shown here. This is uniformity coefficient of materials usually used in the laboratory for physical modeling tests. So what's the task? What do you need to do? Well, you need to do two things. First, to predict the load settlement curve. So you need to predict what is the load settlement curve of this strip footing. You'll apply this here a load of 10, 20, 30, 40, 50 kilonewtons, appropriate stress level in kilopascals on this surface, and you'll have to predict the settlement due to this additional load. In the B part, you'll have to predict the ultimate bearing capacity of this strip footing. So what's the ultimate load that can be applied here before the failure occurs? Probably the failure will occur such that the sliding is coming up here to this slope. So it's not different ultimate bearing capacity as you have a flat area. No, since this is slope, the ultimate bearing capacity is reduced in comparing to the flat ground. So you will have to take account of this slope and predict the ultimate bearing capacity in some kilopascals or similar. Some additional notes: you have to define all the assumptions before that you use to get the results, and you have to give appropriate interpretation. For example, if you use some finite element software for predicting this, you'll have to say, okay, I use this geometry, I put the boundary condition like this, I applied surcharge load like this, I use this constitutive model, I use these parameters, and I get this load settlement response and ultimate bearing capacity. If you use some analytical solution, empirical solution from the literature, you'll have to say, I use this empirical approach, this analytical solution defined by this author from that year, and this is the expression he suggests. I'll combine this beta angle, this width, and this distance from the edge, and I get this information. If you want, you can do one, not only one approach. You can use two approaches. You can try to compare some numerical with analytical solution, with some limit equilibrium solution. You can do whatever you want, but you should have at least this load settlement curve and the value of the ultimate bearing capacity. The deadline for submission is the end of the lecture days. It's about 20 more days. You have to prepare. It shouldn't be so much complicated. It's 2 or 3 pages, just one page showing the assumption of the calculation, second page showing the process of calculation, and the third one showing the results and interpretation of the results. Of course, do not hesitate to contact me by email or during these lectures in next 3 weeks if you have any questions and anything that we need to make clear. If you have some question already now, we can use these final minutes to discuss about this. Anyway, I'll add this to this zip file that I'll upload and send you as a group message so you can download it along with this video material from this day 2 of these lectures. Any questions, any comments? If there are no questions, we'll finish for today. If you have questions, you can contact me by email. If not, let's see you. Actually, not see you, but let's stay in contact next week, Tuesday. Okay, goodbye.
Goodbye.
Bye.